Lipstick starts as a materials engineering problem. You need a stick that holds its shape in a purse, glides at skin temperature, deposits a controlled film of pigment, and survives thousands of twist-ups without sweating oil or snapping at the base. To do that consistently, a modern factory treats lipstick like a precisely tuned composite of waxes, oils, pigments, and performance additives. Built under cosmetic GMP with tight temperature control and aggressive defect prevention, the process begins in formulation and color development because the factory cannot mix until it looks right at production scale. Chemists define the wax structure that sets hardness and payoff, typically blending high-melting waxes for backbone, mid-melting waxes for plasticity, and soft waxes for glide. The oil phase is chosen for spread, shine, and oxidation stability, using esters, natural oils, and sometimes silicones depending on the product claim and regional regulations. Pigment selection is engineered for opacity, undertone, and light stability. And premium lines specify particle size distribution because pigment size changes everything. Smaller particles boost color strength, but can feel dry, while larger particles can sparkle or feel gritty. Before a batch is approved, raw materials enter quality control like incoming parts in an aerospace plant. Waxes are checked for melting profile and odor. Oils are tested for peroxide value and acid value to predict rancidity risk, and pigments are screened for heavy metals and microbial contamination. Every drum is barcode tracked, and because a single wrong lake pigment or fragrance can trigger shade drift, skin sensitivity complaints, or a recall. Weighing is the first production critical step. In high-throughput plants, it's semi-automated. Load cells under stainless weigh stations confirm each ingredient to the gram, and the batch record locks the order of addition because wax crystallization and pigment wetting depend on sequence. Dust capture is built into pigment handling because fine powders contaminate floors, clog filters, and can become cross-shade contamination if airflow is poorly controlled. The main batch happens in jacketed mixing kettles, designed for both heating and shear. Waxes are charged first and melted using hot oil or steam in the jacket. And temperature ramps are controlled so waxes melt fully without localized overheating that can discolor or generate odor. Agitators are selected for the product's rheology. Anchor agitators sweep the wall to prevent wax buildup, while high-shear dispersers break pigment agglomerates. The factory targets a stable melt viscosity because viscosity predicts whether the lipstick will fill molds cleanly or trap voids. Pigments are not simply dumped into the kettle because dry pigment clumps create specks and streaks that show up as defects on the lip. The plant typically makes a pre-dispersion, sometimes called a pigment grind, where pigments are wetted into a portion of the oil phase under high shear. This pre-wetting step forces oil into pigment clusters and replaces air pockets, which is essential because air trapped in pigment agglomerates becomes bubbles during molding. For high-end lipsticks, dispersion is pushed even further using milling. 3-roll mills or bead mills reduce pigment agglomerates down to a controlled fineness, often verified with a Hegman gauge or a similar fineness of grind test. This is where smooth is manufactured. If the grind is off by just a few microns, the consumer feels grit and the brand loses credibility. Milling also stabilizes color, because a consistent pigment surface area gives predictable light absorption, which means the same shade matches across different production days. Once the pigment grind meets spec, it's transferred back into the main kettle and blended into the wax melt. The kettle runs under controlled shear, so the pigment stays suspended and evenly distributed without whipping in air. Many factories run nitrogen blanketing above the melt to reduce oxygen exposure because certain oils and fragrances oxidize faster at elevated temperature, and oxidation shows up later as odor, sweating, or color shift in storage. Performance additives are introduced at defined temperatures because some ingredients degrade with heat or volatilize. Fragrance is typically added late to protect top notes. Antioxidants like tocopherol are dosed to slow rancidity, foam formers, and polymers may be added to increase wear and transfer resistance. But polymer compatibility is tested because incompatible polymers can cause graininess, syneresis, or a draggy feel on application. For matte lipsticks, the balance between powders and oils is engineered, so the surface looks velvet without crumbling. Powders like silica or treated pigments can reduce shine, but too much powder raises break risk. Deration is a core high-tech step that separates modern lines from small batch cosmetics. Even with careful mixing, the melt holds dissolved gases and microbubbles. And those bubbles become holes, sink marks, or weak points in the finished stick. Vacuum deration pulls air out of the molten mass, often in a dedicated vacuum kettle or an inline vacuum chamber. The plant monitors vacuum level and hold time because too short leaves bubbles, while too long can pull out volatile fragrance components. While the formula is being finalized, the packaging line is running in parallel because lipstick is an assembly product as much as it is a chemical product. Empty components, tubes, mechanisms, caps are inspected for cosmetic defects and dimensional tolerances. The twist mechanism must lift smoothly without backlash. The inner cup must grip the lipstick bullet without cracking it. And the cap must seal with consistent friction to prevent drying and contamination. Molding is where the molten lipstick becomes a precise shape, and the molds are engineered tooling, not simple cavities. Bullet molds are typically metal, temperature controlled, and polished to a defined surface finish because mold texture becomes the lipstick surface. The filling system delivers molten lipstick through nozzles into each mold cavity at a controlled temperature and flow rate. Servo-driven fillers control shot volume precisely, because underfill creates voids and overfill creates flash that must be trimmed. Slowing the line, temperature control during molding is critical because lipstick is a crystalline wax network. Crystals form differently depending on cooling rate. If cooling is too fast, you can trap stresses that cause sweating later as oils migrate. If cooling is too slow, large crystals form and the surface can look grainy or frosted. That's why modern factories use staged cooling tunnels or chilled plates with controlled gradients, allowing the bullet to solidify from the outside inward, without creating sinkholes at the tip. Asterisk, after initial solidification, many lines perform a brief remelt on the bullet surface, sometimes called surface refinement. This can be done with controlled heat or infrared to eliminate microlines and improve gloss. The goal is a defect-free surface that reads as luxury under retail lighting, because the consumer judges quality before the product ever touches skin. Demolding must be gentle and repeatable. Automated demolders release bullets with consistent force. Because twisting or pulling too hard creates hairline cracks that only appear later during use. Any bullet that shows tip deformation, surface bubbles, or color streaks is rejected immediately, because fixing a bullet after assembly is slower and more expensive than rejecting it before insertion. Insertion is a precision mechanical operation. The bullet is aligned with the inner cup and pressed in at a controlled depth so it seats firmly without shaving the sides. Depth matters because it affects how much product is exposed at first twist and how stable the bullet is against side loads during application. Some factories use slight reheating of the cup interface so the wax bonds more effectively to the mechanism, improving drop resistance and reducing bullet spin where the lipstick rotates in the cup during use. Once assembled, the lipstick may pass through a flaming station. Flaming is a rapid surface heat treatment that smooths microscopic imperfections and creates a uniform sheen. The flame exposure is carefully timed because too much heat rounds edges, changes the bullet profile, and can alter fragrance perception, while too little heat leaves drag marks visible. Now the line moves into inspection, and modern plants rely on machine vision because humans cannot consistently detect defects at high speed. Cameras check bullet shape, tip geometry, surface gloss uniformity, and shade consistency under standardized lighting. Image algorithms detect scratches, pits, and contamination specks. Units that fail are automatically ejected, and the defect data is logged so engineers can trace whether the issue came from air entrapment, mold temperature drift, or pigment dispersion problems. Asterisk weight control is another non-negotiable. Checkwares verify net content because lipstick is sold by weight and regulations require accuracy. The drift of a few tenths of a gram across millions of units becomes a major financial and compliance issue. So filler calibration is part of routine line verification. Capping and final assembly looks simple, but there where many failures hide. Cap fit is tested because a loose cap allows odor loss and surface drying, while an overly tight cap creates customer frustration and can damage decorative finishes. Decorative components like metal sleeves or magnetic caps require additional checks, because magnets can attract metal dust if the environment isn't controlled, and that dust becomes visible defects on glossy packaging. Labeling and coding connect the physical product to traceability. Batch codes are printed or laser marked. Envision systems verify readability because traceability is only real if codes survive shipping and retail handling. If a consumer reports an issue, the factory needs to trace that lipstick back to the exact kettle batch. Pigment lot, mold, temperature profile, packaging component supplier. The lab doesn't stop working when production starts, because lipstick performance must be verified against measurable specifications. Hardness is measured with penetrometers or texture analyzers to ensure the stick won't deform in warm conditions, yet still glides. Break strength tests measure the force required to snap the bullet at a defined extension, because consumers apply lateral force during use. Payoff tests quantify how much product transfers per stroke under controlled pressure, because payoff defines coverage and wear. Melting point and softening point are checked because shipping containers and retail displays can reach high temperatures, and a lipstick that sweats oil in transit becomes a returns problem. Stability. Testing runs like a parallel production line in miniature. Samples go into hot rooms, cold rooms, and cycling chambers to accelerate failure modes like sweating, blooming, and fragrance loss. Light exposure testing checks color fade, because certain dyes and lakes can shift under UV. Compatibility. Testing checks whether the formula attacks the packaging, because some oils can swell plastics and cause caps to crack or mechanisms to bind. Microbial control is managed differently than in water-based cosmetics, but it still matters. Lipsticks are low-water products, which reduces microbial growth risk. Yet contamination can still occur through raw materials or dirty equipment, and certain molds and bacteria can survive in oily environments. Factories run environmental monitoring, control dust, and validate cleaning, because contamination in a pigmented product is hard to detect visually until it's widespread. Cleaning is engineered for wax and pigment, which are difficult soils. Kettles and pipes are cleaned with heated oils, detergents, or specialized solvents depending on plant design, then rinsed and verified. Many facilities design equipment with minimal dead legs and smooth internal welds, so pigment doesn't accumulate in hidden pockets and shed into the next batch as color contamination. Changeovers between shades are scheduled strategically, often running from light to dark to reduce cleaning intensity, because a single red pigment trace can ruin a nude shade. The high-tech advantage in a modern lipstick factory is the feedback loop between sensors, records, and output. Temperature probes, torque readings on mixers, vacuum levels, and fill weights are logged continuously. If a batch shows increased breakage, engineers don't guess. They check whether wax cooling rates changed, whether pigment fineness drifted, or whether oil oxidation markers rose due to oxygen exposure. That closed-loop control is how the same shade and the same feel can be made across seasons, suppliers, and global plants. What looks like a simple cosmetic stick is actually a controlled crystal network carrying a precision. Pigment dispersion inside a calibrated mechanical package. The factory makes lipstick by managing heat, shear air removal, crystallization, and assembly tolerance so the product glides smoothly, wears predictably, and survives real-world abuse from handbags, heat, and daily use.